everyone, welcome to our webinar today. The topic of this webinar is Energy Storage in Sterling, a Massachusetts Municipal Microgrid. This webinar is a presentation of the Energy Storage Technology Advancement Partnership, also known as ESTEP. ESTEP is generously supported by the U.S. Department of Energy and Sandia National Laboratories and is managed by the Clean Energy States Alliance. And our host for this webinar is ESTEP Project Director Todd Olinsky-Paul, and we've got some excellent guest speakers with us today. Before I pass it over to them, I'd like to go over a few quick housekeeping slides. All of our audience members for this webinar are in listen-only mode. You have a couple of options to join the audio portion of this webinar. You can call in using your telephone, or you can connect using computer mic and speakers. A very important note, we ask that you please submit your questions as you think of them throughout the webinar by typing them into the question box on your webinar console and hitting send. We will be reading through your questions as they come in, and we'll be saving some time for Q&A with the audience at the end of our presentations. So to make sure that we get to your question, please type it in as you think of it. Don't wait till the end. We've got a lot of people that we expect to be attending this webinar, so there should be a lot of questions. Make sure that we get to yours by typing it in soon. Final note, this webinar is being recorded, and you will find a recording of this webinar as well as all of our previous ESTEP webinars on the CISA website at cisa.org/webinars. And we will also send you an email within about 24 hours with a recording of this webinar, and also a link to the slides. And with that, I would like to pass it over to our host for this webinar, Todd Olinsky-Paul.
Thank you, Samantha. Welcome everybody to the webinar. This is Todd Olinsky-Paul. I'm the Project Director for the ESTEP program at Clean Energy States Alliance, and we have a really great webinar today with a lot of very good presenters who were key to getting this project developed and getting the project to where it is now, which is that we've just recently had a groundbreaking, so it's under construction. So I'm sure everybody's very interested to get to that. Before we do that, I just need to give a little bit of background information about CISA and ESTEP for context, and then I will introduce the speakers and we'll go right into the main content of the webinar. I do want to mention that in answer to the question I get most frequently, yes, we do record these webinars. It will be archived on our website following the webinar in its entirety, and also the slides are going to be available on the website. So if you want to review it later or send a link to a colleague who wasn't able to be here, that will be available freely to you, as are all the other ESTEP webinars that we've done over the past several years. So I want to start out by thanking Dr. Imre Zsuk of the U.S. Department of Energy Office of Electricity Delivery and Energy Reliability, who funds our energy storage program, and Dan Borneo, who's with us today from Sandia National Laboratories, with whom we have a contract to do this work. Next slide, please. And I should say that ESTEP is the Energy Storage Technology Advancement Partnership. And just to give a little bit of information about that, ESTEP is conducted by CISA under contract with Sandia National Laboratories. We work with states and municipalities all over the country and with DOE, and the idea is to bring the states and municipalities into a collaborative effort with DOE and the National Lab to produce or develop energy storage projects. And you can see the map. We are engaged with states all over the country on projects. In some cases, we're engaged with them on policy development, and we also are able to provide technical assistance to some of them. And so this is quite a wide-ranging project. And if you want more information, there is a web page for it. Next slide, please. and I think I have it. Here it is. This is just a screenshot from the ESTEP webpage. But the reason I have this up is just to point out that there is a mailing list you can sign up to if you want to get notified about future webinars or reports or other things that we may be doing. There's a big green button there with a red circle around it. You go to our website, click on that, and put your name on the email list. Also on the left-hand menu where you see an arrow pointing to ESTEP webinars, that's where you'll find this webinar archived and all the other webinars that we've done that are there to be reviewed at your leisure. Next slide, please. I'm going to introduce today's panelists, and I believe Dr. Zhuk is not with us. Unfortunately, he's on travel today. So he has sent in a few slides that I will present in his place, and then we'll go on from there. So today we have some slides from Dr. Zhuk, who is the Director of the Electrical Energy Storage Research Program at the U.S. Department of Energy Office of Electricity. And that is the office within DOE that supports the ESTEP project and has supported this Sterling Municipal Energy Storage Project with some added funding and technical support through Sandia National Laboratories. We also have with us Sean Hamilton, who is the General Manager of the Sterling Municipal Light Department and led the project. We have Scott Reynolds, who is the owner and principal engineer at Reynolds Engineering Design, LLC, who managed the project development as the owner's agent. We have Roger Lynn, Director of Product Marketing at NEC Energy Solutions, the battery supplier for the Sterling project. We have Dan Borneo, Engineering Program and Project Lead and the principal member of the technical staff at Sandia National Laboratories, who has provided technical support to the project. And we have Ray Byrne, a distinguished member of the technical staff at Sandia National Laboratories, who conducted the economic analysis for this project. So we have quite a complete representation of different aspects of the project, the technology, the development process, the economics, and so I hope that we'll be able to give you a very complete picture. Before I go into the presentations, one last thing I want to say is please, if you have a question or a comment, type it into the questions box that you'll see on your webinar panel as it occurs to you. Don't wait till the end. We have a great number of people in this webinar, and last count we had 217 people in this webinar. So we're going to get to as many questions as we can. We're taking an extra bit of time today. It's an hour and a half to make sure that we can get to most of those questions, hopefully. And so it'll help me if you send them in as soon as you think of them. Okay. Next slide, please. So I'm going to read Dr. Zhuk's slides because unfortunately he couldn't be here, but he wanted to speak about creating a microgrid-based utility of the future. Next slide, please. And this, what I'm about to read, is something that he actually spoke about at the groundbreaking that was held in Sterling, Massachusetts just a couple weeks ago. He says, the groundbreaking of the Sterling PV storage microgrid was a joyous occasion. On a splendid New England autumn day, federal, state, and municipal partners joined in kicking off a very significant project in Sterling, Massachusetts. The project by the Sterling Municipal Light Department was one of 11 projects selected for funding by the Massachusetts DOER, that's the Department of Energy Resources Resiliency Initiative. The DOE Office of Electricity through Sandia National Laboratory provided extra funding to help increase the size of the project from 1 megawatt to 2 megawatts and help formulate the solicitation for a storage system provider. Next slide, please. The Future Microgrid will be embedded in the Sterling distribution network, linking the police station and dispatch center with 6 megawatts of PV and 2 megawatts of storage. During emergencies, this grid can island and provide mission-critical support. During ordinary times, the microgrid opens up, providing local green energy and local grid services, in particular by shaving off parts of the annual and monthly load peaks, resulting in an expected payback period of less than 7 years. And this is, I should just say, this is the best economic case that we've been able to identify for storage, and it's quite compelling. There are a number of other municipal utilities in Massachusetts that have contacted us wanting to replicate this project, and Ray Byrne, who will be presenting toward the end of this webinar, will go into the details of how that economic case is made. So on this glorious October day, I had the pleasure of joining Judith Judson, who heads DOER, Matt Beaton, the Massachusetts Energy Secretary, Sean Hamilton from Sterling, board members and state representatives in breaking ground for the grid of the future. Next slide, please. And this is the photo of the groundbreaking. And Emery is the fellow in the hat toward the middle of the picture there. So I think that is the extent of Emery's slides. I appreciate his sending them in, and sorry he couldn't be here in person. I'm now going to pass the baton to Sean Hamilton, who is going to give us a bit of background and general information about the project, and then we'll go on from there.
Good afternoon, everybody. I'm Sean Hamilton, General Manager of the Sterling Light Department. This project actually began just about 3 years ago. You'll see later on the slides that we do have quite a bit of solar in our town. In fact, 2013 we were number one in the country. You'll see that in the slide later on. There's a lot of work with the DOER. They came out with the Energy Resiliency Initiative for the state of Massachusetts. They offered $40 million and then broke it down per each city and town based on the $40 million. We applied in the first round and for looking for $2.8 million out of that grant, because knowing that some of the towns would not apply and hoping the funds available would allow us to put our utility scale project in place. We were subsequently denied. And the second round came around. Because we applied in the first round, we qualified. So we then reapplied again. This project's been a lot of work. You'll see through a lot of people involved in this webinar coming up. The town of Sterling, just so you know, we're just a small municipal utility located in central Massachusetts. We have 12 full-time employees. We got a peak load of about 13.4 megawatts, and you know, like I said, we're just a small town in central Massachusetts. Based on what we looked at, we started this project. We looked at what the value of energy storage could bring to Sterling. And right off the bat, the grid resiliency, our police and dispatch center is located just about 1,300 feet away from our substation, so it's right down the road. We looked at we could isolate this on a separate circuit, and through the use of that separate circuit, we could use the charge batteries, and then during the storm or major outage, we could then isolate it to run for approximately 100 hours or so. And having survived the ice storm in central Mass a few years ago, we know that these storms do hit, and these outages do last quite a while sometimes. We had outages, we had people out power in this town in December 11th and 12th, 2008 for up to 14 days. Everything was on the ground. So this project would really help us during those time periods. The other thing that I just mentioned was the intermittent resource of our solar. Solar is a great part of our portfolio. It also can be a hindrance on certain days of intermittent clouds and storms, etc. You'll see in the future a future slide of what exactly that can do to our portfolio. I know Ray Byrne will speak a little more to the regional network service, monthly peak, and the capacity load obligations. But it's a primary cost driver for a small utility like us, and we've worked very hard in the past with load control and demand response and various ways of keeping our peaks down, and this will provide another way for us to do that. You know, of course, and there's energy arbitrage with the off-peak rates being very, very low. We look to charge on off-peak and then use that power during the daytime hours. The timeline of the grant, you'll see right here the first applications I mentioned earlier. That went in April of 2014. And this is the second round. In 2014 December, we awarded $1.4 million on the grant. The grant, I must point out, was not awarded to the Sterling Municipal Light Department. Was rather awarded to the town of Sterling. Through the work and contracts and agreements, we actually are administering this grant for the town. We are a municipal light plant. We are autonomous from the town, but we are a member of the town. In October 2015, as you can see, we signed the contract with the DOER and make sure we had all the required documents that the state was looking for. In that time period, from October through April, We worked with the higher OPM, Scott Reynolds, who you'll hear from in just a few moments on this call, and also our set of design engineers to do the study to make sure what we wanted to accomplish could be done. And today that's going forward. But I think more importantly during this time, we also collaborated with CISA and San Diego National Labs and DOE. What they brought to us as a smaller municipal, it was nice to reach out to some of their expertise and help us refine our RFP. We had initial RFP design and put together, a lot of work put in by Scott Reynolds, but they brought the technical part of that forward that really made it a viable document that I think they're using with others today. And that was key, one of the key points, because going out to bid on this project was new to all of us, and it helped us get us through that process and what we needed to do. As part of that, there was 32 requests for the proposals by various groups. We did find later a lot of them were partnering together, so both sides were asking for the grant. We got down to 4 finalists. This was done through extensive, actually a 3-tiered scoring process through multiple groups. And that process allowed us to go through each one of these proposals that came through and decide how we want to choose them, economic, what if they're providing what we wanted, and also the technical, and where we'd be at the end, or at the end of 5 years or 10 years. At the end of this, NEC, the vendor was chosen. We entered into a contract with them in late August, and as of today, I'm happy to report October we had the kickoff last week, and now the foundation's been poured. That day after the kickoff, we started digging actually the afternoon of the kickoff, and the foundation's since been poured. The trenching is now complete, and as I speak, conduit's being laid throughout the substation. That's going to bring this. That's going to tie this to our riser circuit and also into our substation for control purposes. So we're going pretty well. I think we'll be ready and completed by the end of this week. I'm hoping to see that the infrastructure is complete. And one thing I should point out too, from being a small municipal, as part of a great cost saving to this project, we're doing most of the work. We have a line crew with the transformers, the conduit, the wiring. All this work is being performed in-house, so that's extensive saving that we're not outsourcing a lot of that work, but performing it ourselves. The slide in front of you now kind of gives you a better picture of what we're looking at here. The Shoxit substation up on the top left, you see where the substation is located. If you go further to the left, you're seeing where the police and dispatch facility is. So it kind of gives you an idea of the close proximity that is. The circuit that is located on is actually, there's only 2 or 3 other, I think there's actually 2 other facilities on that circuit. In the event that we had to isolate and get just to that police station, we'd have to open 6 cutouts or approximately half an hour worth of work, and we'd be completely isolated from the batteries to the police station. And also, if you're looking to the right of that, you'll see where microgrid capabilities, because we have a 2 megawatt solar facility on the other end of the street that we could easily isolate to feed from the solar to the batteries to the police station and dispatch center. So there is a good opportunity for us to isolate this in the event that we have to, although we hope we never have to. Everything would line up in place. Just as I said earlier, one of the things that drove this project at the original is you can see where we were in 2013. Little old Central Mass Sterling was #1 in the country for solar watts per customer. As I will show you in a minute, that's a blessing and a curse. You see it's 2015, we're still #7, but we're in some pretty good company, I think. We're very proactive in going after solar. We did most of that is done through PPAs. We have a lot of facilities in town operated by others, but we just buy the output from them and we partner with them to get this done. Here's a good example of what solar can do to you. Looking at the blue line is the one we're focusing on. That's a particular day, September 2nd, 2014, where we're moving right along. You can see the peak of the load climbing in the system. And all of a sudden, around 2 o'clock, as the system was peaking, at the same time, ISO New England is peaking. So that's your annual capacity obligation that we're watching at this time, starting to take place. So what normally this is the period we're trying to shed everything, get all we can shut down to keep our peak as low as possible during this period. But the problem we couldn't control was the solar. At this point, we're looking at a cloud cover. I think it was a thunderstorm that came through at this particular point in time. And the thunderstorm basically brought our load back up over 2 megawatts. Not a good time, probably the worst possible time this could have happened, and probably the best time to have battery available if we had it. And just to show you what the further effect that had, this is the highlighted one you see in hour 14 is what the rates were per megawatt at that exact time that when our power was taking off on us, our demand was skyrocketing. Our costs were also on the market were actually, these are actual locational pricing for that day. So you can see what happened. When we got dumped into the market, we went into the market probably the worst possible time. So again, this quantified to us what storage could do for us, in a situation like this. And this happens more than you think. A lot of the intermittent clouds or thunderstorms during these hot, hazy afternoon when New England peaks. So this allowed us to, storage allows us to get away from that and hopefully preserve for those hours we need it most. And for that, I'd like to say thank you. And you see the list of the special thanks for the commissioners in the town of Sterling and Judith Judson, Dr. Mijuk, and Sandia, Todd Alinsky, Paul Emwick, who's our Mass Municipal Wholesale Electric Company, done a lot of market analysis, and Jerry Carpenter, Jim Frawley, and the technical assistants. This also points out the amount of people it takes to do a project like this. Like I said, this has been a 2.5-year project with a lot of people involved and a lot of help, and I think it's gone pretty well to date. So, thank you.
Thanks, Sean. That was terrific. Just while we're transitioning over to Scott Reynolds and Roger Lynn, who are going to co-present on the technical aspects of the project, I want to give a little context. It was already mentioned that this project was funded in part by DOE and in part by the Massachusetts CCERI, which is the Community Clean Energy Resilience Initiative, a program run by the Massachusetts Department of Energy Resources, which was basically developed after Hurricane Sandy as a way to promote clean, resilient power for critical infrastructure. And that's why this project and, well, there are 19 awards made in that program in the first 2 rounds, 11 of which were to projects that involved energy storage. And all of them are supporting critical infrastructure such as the police station in this case and dispatch center. In other cases it would be a public shelter or maybe a water treatment plant or something of that sort, something that's critical, communications hub. And we've done a lot of work on this, and I just want to mention that in addition to the support from DOE and Sandia, our sister organization, Clean Energy Group, was fortunate to be able to get some very generous funding from the Barr Foundation to support some work with these projects. And as I said, there's 11 awards that were made for projects involving energy storage, and they all needed help in terms of developing project specifications and RFPs, and they're in progress. And Sterling is really the first one out of the gate with the groundbreaking, and so those other 10 are still in the works and not even to the groundbreaking point yet. So that's something that's ongoing work, and I just wanted to acknowledge and thank Barr Foundation for helping out with that, supporting that work, in addition to Sandia and DOE. So let's see, I think we're ready to go now to Scott Reynolds and Roger Lynn for some technical presentations on the batteries and the overall microgrid system.
It's great, Todd. Thank you very much. My name is Roger Lynn. I'm with NEC Energy Solutions. We're the technology provider for the Sterling storage project here. And today I'm going to be talking about the technology underlying the batteries that go into this project. So for this project, when Sean and Sterling Municipal Light Plant approached us, they asked for a full turnkey energy storage solution. And so we've been providing these things, which we call the GSS grid storage solution, around the world, many different places, to utilities or independent power producers for the last 8 or 9 years. And I've installed about 120 megawatts of this type of lithium-ion energy storage solution. What is the GSS grid storage solution? Well, it's an integrated energy storage system. It's a turnkey AC energy storage plant ready to interconnect to the grid. It's a very configurable system using modular lithium-ion battery components. NEC is responsible for designing and manufacturing the control system, which we call AROS, which is basically a way to command in both manual or autonomous mode different ways to dispatch energy storage to solve various problems that you may be seeking to solve, either making money or saving money on transmission charges and such. NEC also designs and manufactures what we call the GBS grid battery system. This is essentially the large containerized battery systems, which I'll go into a little more detail in the next couple of slides. These essentially contain energy storage racks with battery management systems and controls hardware in outdoor rated enclosures. At the bottom of this slide you can see two examples of those. One is in a customized enclosure. That one on the bottom left is actually one we did for Southern Cal Edison back in 2015. That large grayish building is actually the GBS, grid battery system, and then the surrounding equipment are switchgear, transformers, and power conversion systems. Included with the GSS is the power conversion system, or the inverter, of course. We source these from leading manufacturers all around the world and put them in place depending on the site and the project requirements. And we also include thermal management units, air conditioning, or water chillers for battery cooling to make sure that they stay within the parameters required for optimal life and service and performance. There are three major functional components within the GSS. We described within this dashed line some of those, but this is more of a high-level outline of those three components. The first, of course, is the control system. This is the brains of the operation, essentially senses what you're trying to do. In this case, let's say reduce transmission charges, so we can use AROS controls to sense the power flows and adjust the output of the batteries accordingly to manage to a threshold or a limit of power absorption from the grid. The controls tap both into the grid battery system, which is the DC energy storage system, essentially the batteries themselves, as well as the power conversion systems on the bottom right, which of course convert DC to AC. All this is managed by an operator, which can either set it again into manual mode for scheduled charging and discharging according to time or other triggers, or it could be an autonomous mode, for instance, performing something like frequency regulation, where you are responding to a AGC signal or some sort of control signal from some system operator. And of course, the physical connection to the grid is AC. The power conversion system sits in front of all that. Cooling is a fairly important part of our systems. Thermal management of the batteries that are contained within is critical for ensuring the durability and the service life and the performance of the systems. And so we take great care in analyzing the applications, making sure they use the right number of batteries, right size of batteries, in addition to the right amount of air conditioning or cooling required to optimize the system. So a little bit more as we dig further down into the installation, a little bit more about the GBS battery system. What we're using for the Sterling project is a standard containerized lithium-ion battery. You can see a cutaway image of it here. We call this a GBS LD 53-foot container. It's comprised of lithium-ion battery racks, which you can see lined up in here. This cutaway shows only one row of the racks. There's actually another row that's on the other side of the container. So there's two rows of racks inside the container. We can fit up to 4 megawatts and 4 megawatt hours in a single container. However, for this case, we've outfitted and configured it to be a 2 megawatt, 3.9 megawatt hour energy storage system. The particular technology here is something we call LD, or long duration. This lithium-ion chemistry is designed for 1 hour of energy storage or more, and we're using a very mature lithium-ion technology, one that we've installed and deployed in the field for several years already for other utilities around the world, including installations in Hawaii, England, and Spain, etc. All of this is actually assembled here in Westborough, Massachusetts, so it's all assembled locally. and all the expertise and the senior leadership of the company is located here within Massachusetts. So you can see some of the features here. In addition to the energy storage, there are the roof-mounted air conditioning units, DC isolation switch, which houses some of the main fuses and breakers for the battery container itself, and then a fire suppression agent container shown here, which is part of a larger integrated fire suppression system, which is clean agent based with smoke and heat detection. One of the things that we stress in our designs of all of these equipment, this is not your average everyday shipping container. We take great pains in designing this for the utmost in safety and reliability. These fire suppression systems and other features within the container assure safe operation, and in the event that any hazards do develop, we do have both the container itself and the fire suppression system that help to prevent anything from escaping the container. Also inside the container are the control racks, which help to manage the battery systems, and then the battery management systems within each rack itself handle the battery cells inside the rack, keeping them in line, equalized in state of charge and voltage, and report back all the voltage, temperature, and current of the underlying cells. So it's a fairly mature technology, something that was important for this project to have something that was proven in the field and would fit well with the application. So from here, what I'm going to do is just turn it over to Scott Reynolds, and he's going to go over some of the project specifics on the one-line diagram and some of the operating modes. So, Scott, please go ahead.
Sure. Thank you, Roger. So I'll pick up from where Roger left off. When NEC delivers the storage container and the PCS, and we had to integrate it into the existing Sterling grid. So essentially, Sterling is providing a step-up transformer between the PCS to take the AC output from the battery storage solution and step it up to their distribution level voltage, which in this case is 13.8 kV. In addition to that, one of the requirements to provide power to the cooling and the control systems for the GDS container is an auxiliary transformer. So we've taken a distribution feed from just outside the substation and brought it into a riser pole and into a pad mount transformer, loop fed the pad mount transformer over to the auxiliary transformer, and then brought those two separate feeds over to the NEC provided equipment. The equipment also requires some controls inputs, such as voltage measurements and current measurements from the interconnection point to the utility, and that information is fed back through a data connection. You can kind of see that on the left of the page. There's a multi-mode fiber that we're running between the Sterling substation control house and the Aero system in the GSS container. So those three things are essentially the connection to Sterling's existing system. It's the actual power connection to the grid, the auxiliary power connection to power up the unit, and the data connection in order to be able to exchange information back and forth between Sterling and the NEC system. So next slide. So this is essentially the setup that we had originally envisioned. As a microgrid, the utility takes its power from the 115 kV, and there's a step-up transformer in the substation, and the distribution system throughout the whole town is 13.8 kV. So the town has critical loads, non-critical loads, and then the PV generation. And you can see that at any time, all of them are connected together working together. And if we were to lose the 115 kV connection and the substation goes down for an emergency event, we would end up with switching over to the microgrid resiliency mode of operation, which is shown on the right of the page here. In which case, we would disconnect all of the non-critical loads, and we'd disconnect the PV generation, and we'd start the system back up under the islanded mode. And in that mode, the GSS battery would essentially act as a grid reference. And then you can bring up the critical loads in the emergency response facilities, and they really would act the same as if they were connected to the normal grid. We've got several days worth of storage that they can ride through an event like that. There does need to be a process where you bring everything down, and there's a short outage of about a half an hour, and then you can come back up with the critical loads energized under resiliency mode. I just want to say one more thing. We did consider connecting this battery unit directly to the substation bus, but in the end, we decided to take it from an actual connection from the street on an existing feeder. And I think that's an important point to mention, just because it reduced the interconnection cost by quite a bit, and we realized that the substation offers security inside a fence, and that's a good thing. But if there's other folks that would like to do this type of thing, it doesn't necessarily have to be at the substation. As long as you can get that, those three connections, a way to exchange data, a way to connect to your distribution system, and a way to serve some auxiliary power, this can really be done outside of the substation, throughout the town, throughout where you might have available, and things like that. So just one thing to point out about how we connected this to the grid. So with that, I'll turn over to the next presenter.
Okay, thanks very much, Scott and Roger. I think Dan Borneo is up next, and just to let folks know, we are getting quite a few questions. We'll get to a lot of them, I believe, given how quickly we're moving through this. So keep sending your questions in, and we will answer as many as we can. Okay, I'm going to turn this over now to Dan Borneo from Sandia.
Yes, good morning. Dan Borneo, Sandia National Labs, and I lead the Energy Storage Projects Group funded under Dr. Emery Zook. And today I just want to give a little overview of what we do and your federal tax dollars at work, and I hope in a good way. So we're the industry acceptance, and basically we're trying to encourage investment in energy storage through field deployments. And so we work with everybody. We work with national, international, the Department of Defense, the state energy offices, as Todd explained, other national labs, utilities, from soup to nuts. We do grid analysis, some projects. We support initiatives from the state, the international, and then we also do the public information programs such as this webinar. And a little bit more detail into our capabilities. So we do energy storage applications, sizing, and technologies. As you're going to see with Dr. Burns' presentation, we look at what size we should be installing, what duration we should be installing, what technology is best utilized for the applications that will bring the most return on investment. And we're developing some internal tools that we hope in the not too distant future we're going to be making public. So then we're going to take these tools out to the engineering firms and provide them this tool so they can then start doing the same type of analysis. We also do the project development and implementation process, have many years of experience in construction, have good experience with the RFI, RFP process, project design, specifications, data acquisition systems. For us, that's the most important part. When Dr. Zook provides funding for a project, it is so we can get the data, do the analysis on the data, try to learn, and then propagate that learning to the next projects so we continue to grow the energy storage industry. And then we provide technical support through construction, commissioning, the startup, the testing for the different applications. And then as I said earlier, Dr. Byrne does the system analysis, so we're always looking at how we can improve this. And Todd showed this map in his presentation, so I won't go over it. But these are all our projects, and our goal is to have a PIN in every state. So if you are from a state and you do not see a PIN there, and you're interested in energy storage, give Todd a call, and we'd like to talk to you about future projects. And that's it for me.
Okay, thanks, Dan. We're going to move on to Ray Byrne. I just want to mention that Dan spoke about some tools. There's a lot of development of tools within Sandia. One thing that pertained to this project in particular was that a bunch of the participants in the project, including Sandia, DOE, CISA, Reynolds Engineering, Sterling Municipal Light, and others, worked on a procurement document for energy storage that's intended to help other municipalities and municipal utilities understand what needs to go into an RFP to, you know, when you're looking to put together a system like this one. And as far as we could tell, there really wasn't any kind of guidance document already out there. So that is something that was published by Sandia. It resides on their website. I think we also have it on a link to it on our website. So if you are on the webinar and you're representing a municipal entity or other entity just looking to perhaps put together an RFP for storage, you might want to check that out. And so with that, I will now pass the baton to Ray Byrne, who is going to talk about the economics of the project. And we've had a bunch of questions about that piling up. So Ray, I think there's a lot of interest in this aspect of it.
Okay, thanks, Todd. So for the Sterling analysis, we looked at several different potential value streams. First was energy arbitrage, just buy low, sell high. The next was a reduction in monthly network load based on reducing your monthly peak hour. And then we looked at reduction in capacity payments in the poor capacity market, and that's based on reducing your annual peak hour. Then we also looked at grid resilience and then frequency regulation. So for arbitrage, that's just your traditional buy low, sell high application. We looked at 33 months of data from January 2013 to September 2015. We performed an optimization using perfect foresight, so that assumes you know the future. We've done some additional analysis that shows typically you can harvest like 80 to 90% of that predicted revenue with usually a pretty simple trading algorithm. And then the table below just shows for different 1 megawatt plants, if you change the capacity from 1 to 2 to 3 to 4 megawatt hours, what your typical monthly savings would be. So for a 1 megawatt hour plant, the average monthly savings was around $3,300, and the annual savings was around $40,000. The next potential value stream was the reduction in regional network service payments, and that's a monthly payment based on a maximum load, and it's used to cover transmission facilities in ISO New England. Right now, the current full rate is $98 per kilowatt a year, but if you look at the table, let's see, you need to hit the hour too for this application. If you're reducing your load in the wrong hour, it really doesn't provide a benefit. And then also having a multi-hour or more capacity doesn't really provide an increase in benefit, but it does increase your odds of hitting the hour. I've got some slides towards the end that just talk about the odds of hitting the hour given different sizes. And then one note about this application, it is open to potential policy changes. There could be some adjustment in the future where maybe there would be a load adjustment and you wouldn't be able to take this as a benefit. But anyway, for potential savings as a function of power, 1 megawatt-hour system or 1 megawatt system would save you about $98,000 in annual savings, whereas a 4 megawatt system could reduce your load enough that you'd save about $394,000. And the next potential value stream is reduction in payments to the forward capacity market. So each load serving entity is responsible for a fraction of the forward capacity market obligation, and it's based on the peak load over the course of the year. One thing about this particular benefit is that the rates have been increasing. So if you look at the table to the bottom left, 2010, 2011, it was $4.25 per kilowatt month, whereas it's projected to go up to $9.55 per kilowatt month in 2018, 2019. And if you look at the trend, the prices were fairly low in the past, but they're trending to be much higher in the future. So the table on the bottom right just shows some potential savings given a different price for the forward capacity market. And for 2018, 2019, where it's $9.55 per kilowatt month, 1 megawatt system could result in potential saving of around $157,000. So this is another significant potential value stream. Then we looked at grid resilience. We didn't attempt to assign a value for that yet, but we just looked at how long a 10 kilowatt critical load could be run based on the megawatt hour capacity of the system. So a 1 megawatt hour system could provide 4 days of backup. Through a 4 megawatt hour system would provide up to 16 days of backup. And then we looked at frequency regulation as the last potential value stream. For this, we did some optimizations with market data from several years. This plot shows just 2015 data. The bottom of the chart, which is a little cut off, it looks like, in the slide presentation, the axis is the capacity in megawatt hours, and the y-axis is the gross revenue in hundreds of thousands of dollars. So one thing you'll notice that there's a knee in the curve for all the plots, and we go from 0.25 megawatt system all the way to a 2 megawatt system. But pretty much the knee in the curve always occurs when the power rating is 1/2 the capacity rating. And that just, it's because you want to hang out at a 50% state of charge and be able to provide regulation up and regulation down. So for example, a 4 megawatt hour system with a 2 megawatt power rating can hang out at 50% state of charge and provide the full 2 megawatts up or 2 megawatts down for the full hour. So there's a knee in the curve or the top line, which is a green dotted line with the circles. But back to the more realistic size, it's just a 1 megawatt hour system. I'm sorry, a 1 megawatt, 2 megawatt hour system can provide about $200K of annual revenue. So this is another potentially significant revenue source. So as far as the impact of capacity and hitting the monthly peaks, if you had no other information except for what the previous peaks were in the past, and just used a simple algorithm where you went with the highest probability of the hour for you're trying to hit, this shows the distribution of the monthly peaks for 2003 to 2013. So you'll notice it's pretty spread out. Hour 19 has about 28% of the historical peaks. Hour 17 has about 16%. And hour 15 has about 14%. But if you just used a really simple algorithm, you need quite a bit of capacity. You basically have to turn on from the 11th hour to the 21st hour to have a pretty good chance of hitting that peak. So this is one area we're starting to do a little bit more work is, what other types of algorithms could you use to hit these monthly peaks? And then this just shows the cumulative density function for the monthly peaks. So if you had a 3-hour system and you'd only be able to hit about 60% of the peaks based on just using historical averages. So there's hopefully some better algorithm that you can use to increase your odds of hitting the peaks for the months. This slide talks about the annual peaks. Here we are a little bit more fortunate. The annual peaks are pretty much distributed over 3 hours historically, with the 15th hour being the greatest occurrence, with about 69% of the peak hours being in the 15th hour. So the good news here is that, you know, it wouldn't take much capacity to guarantee that you're going to hit the annual peak just based on historical data. So this is just a cumulative density function. Even with a, a 1 hour system, you'd have a 60-some% chance of hitting the peak, and with a 3 hour system, you could pretty much guarantee you'd hit the peaks as long as things stay like they were in the past. So in summary, we've looked at several different potential revenue streams. Arbitrage, it turns out, is more synergistic with the two peak shaving applications because when you buy low, sell high, you're typically discharging during the peak hours. So we grouped those together, and the table shows the potential benefits for a 1 megawatt-hour system. So arbitrage was around $40,000, R&S payment was about $98,000, and the forward capacity market obligation was around $115,000. So that gives you around $255,000 for total potential expected revenue, and that's ignoring frequency regulation. So right now we're looking at some approaches to incorporate frequency regulation. For example, in 2015, it was around $200,000 in potential additional revenue. But because it is contrary to the two peak shaving applications related to the R&S and FCM obligations, we're going to have to do a little bit more analysis to harvest that additional revenue. But the great news is there are plenty of opportunities for revenue, and for a capital cost of, say, $1.7 million, you'd get a simple payback of about 6.5 to 7 years. So like Todd said earlier, these are some of the best numbers that we've seen for any application.
Okay, is that it? Is that it for your presentation?
Yes, that's it.
Okay, thanks very much, Ray. So obviously we've had a lot of very good information, and we have a lot of very good questions from listeners, and we have some time to address them, which is great. Before we go to just start going through this list of questions, I just want to throw this out to Sean and Scott primarily. Obviously the project's not complete, but at this point, what have been the hurdles, and what were the challenges so far, and how did you address those? If you could just pick a couple of things that stand out, I think it might be of interest to people who are developing similar projects.
I think you can go first on this. I think the biggest hurdle was pulling everything together, finding the sources. There's not a lot of information out there for these projects to latch on to build the RFP, which you spoke about earlier. The process of, it's a broken up thing. You've got the interconnect, you've got the batteries themselves, you've got the siting, you've got the grant applications you go through. Then you've got the meetings, you've got the building inspectors, you've got the electricians, the fire departments. There's a lot of parts that go along with this project. I think one of the most challenging was doing the RFP to make sure we get it right. Because when it goes out and people are bidding or submitting proposals on this, it was not a bid, it was a proposal. I got to clarify that. You want to make sure you get it right in the first shot. And I think what you mentioned earlier was critical, that we worked. Scott had done a great job preparing it. We put the Massachusetts procurement laws to it, and Sandia and CISA and the others put the technical aspects onto this, on the DOE, Emery and his team. That was the hardest part, I want to say, about the project. Waiting the timeline, of course. It's been almost 2.5 years. But as far as project goes, it's not too long, but it seemed long to me.
Yeah, I'll add to that. I think since it is kind of a emerging technology and it's maturing very quickly, I think keeping up with the technology that's available out there, writing the RFP in such a way that you're getting tried and true technology, but you're not getting ancient technology, and you're not a guinea pig, is kind of was a balance we had to make. And when those bids come back in, you get various proposals for various different approaches to the project, and evaluating what is most important to you as the customer, and what you value and how to score that. So we ended up going to a scoring system to try and create a level playing field and figure out which vendors offer the most advantage to Sterling. So I think that part was the trickiest part.
Great, thank you. So somebody has written in a question, was this project modeled off a similar project in the country? If so, where can we find information about this? I'm going to, I think, maybe ask Sean first, and then others may have comments on this. Was there something that you were looking to when you were sort of developing this concept?
Actually, we weren't. Actually, we started on this a while before the project even came about, was looking at how to solve the intermittent resource problem of the solar. We looked into the batteries, and the project built from there, but we really didn't have anything. Like I said earlier, we didn't have anything to go on. We kind of built our own ideas into what we wanted to do, and then working with everyone, kind of put them all on paper.
Okay. I should just mention that in terms of the economic case here, we also had good fortune to work along with Sandia and DOE Office of Electricity with Green Mountain Power on their 4 megawatt energy storage solar microgrid in Rutland, Vermont, and that's been up and running for a while, and they actually, as far as the economics of using the storage behind the utility meter to reduce capacity and transmission cost obligations to ISO New England, they were kind of the first ones that I know of to do that. So in that aspect of it, there was an example to look at, and we're just starting to get data from that project. Okay, so yeah, go ahead.
Could I add something to that?
Please.
For other projects that are similar, that they might want to go to the Sandia Global Database website and check out other projects, and they get an idea of what else is going on.
Good suggestion. DOE Energy Storage Database.
I would add to that. We've seen a lot of different projects as an energy storage solutions provider. So applications like resiliency / microgrid, applications like voltage regulation, like peak load reduction or scheduled power dispatch. These are all common requests. What we find is a challenge is that the rules are so different in all different parts of the country, and so that where peak load reduction may make a lot of sense here, it makes less sense in other parts of the country just due to the difference in policy and market rules and regulations. But I would say that in most cases, when we're approached with a request to put in energy storage, what we start off with is maybe 50-50 shot of what we end up with. And we do a lot of analysis to understand what the customer is trying to accomplish, explore around that, see if there may be other value streams that can be tacked on to the project scope, and then ultimately configure and size the battery system in megawatts and megawatt hours for the application modes as well as the targeted service life, and all that stuff is part of the scope that we take on.
Okay, thank you. I want to go to another question here. Somebody, and this is specifically about the battery, so I would think maybe Roger would be the person to answer this. Please explain how often the battery system can be cycled. For instance, would it be a good resource to use for 2 to 3 hours each day during the hours that have the highest power cost? Would daily cycling of the batteries affect the warranty?
Yeah, so that's a great question. There's a lot of different ways you can cycle batteries. We use lithium-ion batteries from world-class suppliers. We have a very intimate knowledge of how these things age, how they wear out over time, and certainly the types of batteries we use are analyzed against the duty cycle. And I call a duty cycle is how hard are you driving the battery, right? The analogy to a car is if you have a lead foot and you accelerate and brake very hard, you're going to wear out faster than if you drive very carefully. So the same thing goes with duty cycles for batteries. The batteries we use are designed for lots of cycles. In this case, I think we've got lithium-ion batteries that'll last for 4,000 or so full discharge cycles, meaning that if you have, in this case, 3.9 megawatt-hours in the battery, you can charge and discharge 3.9 megawatt-hours and do that thousands of times before it reaches an end-of-life condition. And that's the other part of the scoping of a service life of a battery is, what constitutes end-of-life? When is it done? When can it not deliver what it was meant to deliver? And that gets into some of the scope of the application. So, for instance, if you're trying to provide a peak load reduction and the requirement for doing that peak load reduction or peak demand reduction is 3 megawatt-hours, then that might constitute your end-of-life condition. And so thus you might size it to be 3.9 megawatt-hours up front so that it provides at least 3 megawatt-hours through a 10-year service life. There's a lot of nuance in the cycling of the batteries, and whether you're using a lithium iron phosphate battery or a nickel manganese cobalt battery, they all have sort of different characteristics. And so the way we kind of even everything out or look at the total cost of ownership is by putting the battery technology itself and the duty cycle into a levelized cost type of analysis. And that can kind of spit out what the best battery type would be for the application. But for instance, cycling it 1 time a day, 2 times a day, 3 times a day, that constitutes whether you drive your car to and from work 1 time a day, twice a day, or 3 times a day. So the wear and tear will add up in that same manner.
Okay, great. Well, that leads to another question, which is, does Sterling dispatch the battery system themselves during peak hours, or does a third party manage dispatch of the system?
At this time, Sterling will be doing all the dispatching and programming. I think Roger said earlier that it could be pre-programmed to hit certain thresholds also. That's something we'll be looking into.
Yep, there's both scheduled power dispatch mode and I think peak load reduction mode. So scheduled power is basically what it is. You schedule it to operate how you would want it to operate against certain triggers, time being one of them. 3 o'clock do this, 4 o'clock do that. The other operating mode is a peak load reduction mode, where you operate in PQ mode. You would manage to a threshold. So you would charge and discharge to keep peak demand at or below a threshold setting, and where that threshold is set is, that's really the trick of it, is getting that right.
I should add, we have had vendors offer to manage this for us, but we haven't entertained that yet.
Okay, thank you. Somebody wants to know what steps have been taken to ensure the safety of the energy storage system, and what training has or will be provided for first responders to address hazards and potential emergencies involving the batteries.
Yeah, so this is Roger with NEC again. We design a lot of different layers of safety into the system. You saw maybe on the cutaway diagram I showed calling out of the Clean Agent fire suppression system that is installed inside the container. That is designed to, of course, put out any incipient fires that might happen due to some sort of abusive operating mode. All of our controls do protect against all those modes, and I'll say at the risk of jinxing myself that in the 120 megawatts we've deployed, we have never had to use the fire suppression system even once over this 8+ years of operation for utilities around the world, independent power producers. Some of the very early projects that were done by AES were using equipment that we've designed and in operation in South America and here in frequency regulation in PJM. So haven't had to do that yet, but we always get asked the question, and this always comes up during the installation when we're going through the permitting process. We're going through sign off by, let's say, the local fire marshal or fire chief, fire department. One of the toughest situations we had was when we did an installation in Hawaii on the island of Maui. And about that same time, this is I think late 2012, we were doing the installation. Another battery system from a different company, also in Hawaii, this one was on Oahu while we were in Maui, actually caught fire and shut down a large wind farm up there. And so, the fire marshal and state senate there really had a hard time understanding how the other project that we're currently in construction, including our own, were going to be safe. And so as a result of that, we had to disclose a lot of the training that we provide and instructions we provide to first responders for fire departments to say, if something's going on, there's smoke pouring out of the containers, the batteries, what do we do? And we provide a one-page simple instruction sheet for first responders, as well as a more detailed presentation to first responders, fire, paramedics, etc., so they can understand the nature of the hazard. And of course, this is a big topic, not just back in 2012 in Hawaii, but now more so in very dense urban environments like Southern California or New York City, where we've done some work with FDNY to help them understand some of the hazards, the nature of the hazards posed by lithium-ion batteries.
Todd, if I might add to that, we actually brought the fire department in. As you can imagine, this question was brought very early to us. We brought the fire department in very early into this project, and through the process, they've met with the vendors. They've seen the diagrams of what's going to be inside of the thing, and they will be receiving specialized training at the start of this project when it's situated.
Okay, great, thank you. So somebody wants to know how you do the cutout to isolate the police station in case of a grid outage. Is that manual or is it automatic? And also, does the battery support all the other customers on the circuit?
The first answer is no, it's not automatic, it's manual. It could be made automatic. We've chosen this time not to. That could be a future consideration. Right now, as far as the distribution circuit-wise, we'd have to open 6 cutouts, which takes approximately 10 minutes to pull those 6 cutouts. That would isolate the circuit and then would feed direct from the batteries right to the police dispatch center.
Okay, great. Somebody is asking, is the AROS control hackable? I guess this is a question about cyber attacks. Is there vulnerability to cyber attacks? Or is there anything that needs to be done in particular to make sure that doesn't happen?
Well, I would say that I personally am not an expert in cybersecurity. I can say that we have designed AROS to operate with all the, I guess, industry norms for security. We are looking at the NERC SIP protocols for critical infrastructure protection, which do encompass cybersecurity for the control systems. And it is a question we get asked a lot. I just, is it hackable? We haven't had an instance of that before. Again, in the 8-9 years of operation and dozens of sites around the world. But I would say that if somebody's really wants to get into it, I would say that there's always that possibility.
Okay, thank you. There are a couple questions about the battery. One is, how was it sized? Was it sized to optimize operation of the system? Was it sized for in some other way? And the other is, what's the round-trip efficiency and what are the house loads and their impact on the efficiency?
If I may,
okay, so yeah, go ahead.
I'll let you parasitic load and everything else. Primarily what we did is we went out for a megawatt. The first initial idea was to go out for 1 megawatt, 2 megawatt hour system, and we also had it for additional biddings or proposal purposes to see what a 2 megawatt, 3 megawatt hour, and 2 megawatt, 4 megawatt hour to get a price break and see where these things fell. And that was the initial way we started, looking to try to take a piece of our solar project, at least 2 megawatt hours of them out of the picture and kind of neutralize them a little bit if we could. That was the start. We ended up with the 2 megawatt, 3.9 megawatt hours because this was Scott Reynolds. To make sure that the project, maybe you can explain this a little more, Scott, how you came about this, is to make sure the project met the full, what it would meet in 5 years. If we meet the full 3 megawatt hours in 5 years and how we got there. And that allowed for the larger size, 3.9 megawatts. I hope I explained that okay. Maybe you cut in on that, Scott.
Sure, yeah. So kind of along with what Roger was talking about earlier with end of life, we wanted to make sure that we had at least 3 megawatt hours at the end of life. So we determined the end of life as 10 years, and we asked each of the vendors to do their own degradation calculations that they would have to do to determine beginning of life capacity to meet what we were looking for at the end of life after 10 years. And we had to give them assumptions on how this was going to be used, how it was going to be cycled. Like Roger was talking about, if you cycle it differently, you're going to get different results in your degradation. So to make a level playing field, we had to give them the assumptions about how it was going to be used, and then told them we wanted 3 megawatt-hours at the end of life, at the end of 10 years. And each of the vendors came back with, what size they would have to start with at the beginning of life in order to make that happen, and accordingly, what the price for that size would be. So that's how we kind of ended up. And then, you can kind of wade through those results and figure out where you're getting your best bang for your buck.
And I think the last half of the question was with respect to parasitic loads. What constitutes parasitic loads? What else is taking power away? So I guess the biggest one of all these is going to be the cooling system itself. That probably consumes the most electricity in operation of the system. And depending on how what the temperature is inside, and also what the duty cycle, again going back to how hard or how intensely we're driving the battery. How hard that duty cycle is, that aux load can vary significantly. For this one, I don't know the exact round trip efficiency of this particular project. Let's say in a peak load reduction mode, which I assume would be running at a roughly a 2-hour rate, I would imagine. But we've had systems out there in similar applications where the round trip efficiencies all in range from, let's say, 80% to like high 80s, including all the thermal management and losses within the battery itself, within the power conversion system, within the transformer. If you want to kind of draw the line around that, that set of equipment. In higher rate operation, the round trip efficiencies would typically drop, but I imagine this one we'd be probably mid-80s. But I'd have to go back and check and see what our modeling guys had penciled out for this one.
Yeah, and so that's another thing that to add to that, you have to make sure you specify in your proposal how you want efficiency to be calculated, so you can compare apples to apples. Do you want them to include the the auxiliary power that's consumed by the cooling, or not? Do you want them to measure that round trip efficiency at the output of the inverter terminals or the high side of your step-up transformer? It just makes sure that's all defined so that everybody calculates it using the same assumptions.
Okay, thank you. Here's a question about siting and permitting. What, if any, special permitting and inspection challenges did you encounter, and did these lead to delays in the project, or do you expect anything of this nature to lead to a delay in the project or increased cost?
I can speak to that. No, we didn't have any special permits. We went out and met with the building inspectors, Conservation Commission, wiring inspectors. We have a licensed electrician on board, so he'd be pulling the permits for the panel we had to put in. Conservation was not an issue, and building, where we just actually had 4 piers replacing this on, it wasn't really a building per se. So building inspector was fine with what we were doing. It's all located inside of our substation. There was no additional groundwork being performed except for the excavation for the piers in the base, so it really wasn't a lot as far as excavation or building wise. At that point, we just brought in a container and put it on top, or will be.
Okay, thank you. Go ahead.
I think from a permitting perspective, the fact that Sterling put it inside the substation helped quite a bit. There was really no land to disturb other than what they already had as a substation. So.
Yeah, we were there. It's essentially sitting on gravel. It's within a perimeter fence, and it's part of the substation. So the questioner did mention environmental issues. I would assume there weren't any. There doesn't seem to be any potential for any kind of environmental disturbance from this thing. And if anybody's ever seen these, it just basically looks like a shipping container put on a pad. So I'm going to move on to the next question, which is around the disconnecting the PV system. I'm not sure I understand this question. It's why do you disconnect the PV system if there's a problem and you want to go on battery? I guess that means in case of islanding. Do you disconnect the PV system in case of islanding? It seems like you wouldn't.
I think the question to that would be, when we would use the PV system? I think we're looking at a storm that the system's down, the transmission's down. We've got PV, we've got batteries, we've got a control house. Could we get the three of them back going to working together? You need a source side on your PV, obviously, to operate. So once you get a line from your substation to your PV that sees the source side, it would then operate like it normally does. Again, then backfeeding into the 13.8 system, which would then in turn charge the batteries, which could then in turn feed the police station. It would be under a situation where everything is down, the system is out, transmission's done, and the three can be tied together. There'd be no other reason we take down either one of them, any one of them.
Okay, thank you. Question, this is directed to Scott Reynolds. Can the battery discharge and at the same time charge from PV if PV is available, or serve the critical load while conserving battery charge?
So if the PV was connected to the same distribution line, and I'm assuming we're talking about in resiliency mode where the rest of the town is out and you're just trying to serve the police station, then it would be a net to the battery. So the battery would either, if the PV, whatever the PV was generating, whatever the police station was using, the battery would charge using the rest of it, and then as night fell, the battery would kind of turn the other way and start providing power to the police station to serve their load overnight. I think hopefully that answers the question.
Okay, thank you. A couple of people have asked if they understand correctly, is there a 30-minute delay in obtaining resiliency after the loss of grid power?
Yes. Yeah, it's a manual. It's a manual operation to go pull those cutouts.
Okay.
So that's why we built in a 30-minute delay.
Great. And so somebody wants to know how much more costly or problematic would it have been to allow for a seamless transfer so that you didn't have a 30-minute delay?
I think one thing to point out, Todd, is that this building is on a generator, so they will have power carrying us over to that transfer.
Okay, so that during that 30 minutes, the police station will be powered.
Correct. The idea is based on, back to Sandy, where a lot of if they couldn't get fuel with the generators, the generators constantly full and maintained, and they would have operational time for the 15-20 minutes it'll take to pull those cutouts. They would operate, and then at that point we could pick them up from that point on and conserve their fuel for the future, what have you.
Right. Okay.
Yeah, I mean, you'd have to have automatic devices at each one of those disconnects instead of just cutouts. So it would add, quite a bit of distribution system upgrades if somebody wanted to try and implement that on their own project. Just keep that in mind, I guess.
Okay. Speaking of costs, and I was just curious, maybe Ray can speak to this, the payback period that was mentioned being less than 7 years, is that payback including the state grants and the federal grant, or is that payback of the project cost disregarding the grants?
Okay, so this is Ray. I just used a number for a typical 1 megawatt hour system, and then assumed $200 and some thousand a year in revenue to get that payback. So I did not use the actual size of the system that was purchased, and I did not incorporate the additional funds from DOE and the state. So the payback should be significantly faster if you include the additional funds.
Okay, and just following up on that for a moment, you did the modeling on a 1 megawatt hour system. Assuming there are economies of scale, have you looked at how the payback would, how much shorter the payback period would be for, say, a 2 megawatt or a 3 or 4 megawatt system?
So just talking in general, as you increase the power rating of the system, say you go from 1 megawatt to 2 megawatt, you will double your potential benefit from the regional network services and the forward capacity market reduction in payments. But it'll have a smaller effect on arbitrage, and then frequency regulation. It'll have a pretty significant increase. So it doesn't scale linearly, but I guess that didn't quite answer your question, but it will get better, but it's not linear.
Okay, but so it sounds like even without any subsidy or any grant, you could achieve a pretty reasonable payback given the economic case for this type of system if you're a utility in ISO New England.
Oh yes, and that's why we were really excited about the analysis on this project. It's one of the best paybacks we've ever observed, and yeah, just without any kind of subsidies, it looks like 6-8 years it can potentially pay for itself.
Okay, thanks. But by the way, we mentioned that you did the economic analysis. Is that coming out soon? That'll be public, right?
Yes, we're submitting a conference paper to the IEEE Power and Energy Society meeting, and we should have a draft that should be releasable pretty soon.
Okay, great. And we'll make that available as well through our website, I think, once that's public.
Yeah. Our deadline is November 7th, so it has to be out by then.
Great. Okay, moving on to more questions. Somebody wants to know, has the fire suppression system in the NEC battery container been tested in any full-scale fire scenarios?
Yeah, this is Roger. We haven't tested the full container. We've done scale simulations here at our facilities in Westboro. Burning down an entire battery that size is a little expensive.
Okay, thank you. I just want to note that there is a project right now being carried out in New York City by the New York City Fire Department and Con Ed and NYSERDA, where they actually are going to burn down a variety of batteries and analyze the results and how the response systems work and so forth. So that's a topic of some interest, and I hope we'll have more information about that soon.
Yep, yeah, we're aware of that.
Okay. So somebody wants to know more project economics, battery cost per megawatt hour, maintenance cost, and cost of ancillary equipment. Is there, I don't know who would speak to that. Would that be Roger or Scott?
Yeah, I guess so. On the battery cost side, there are varying cost metrics out there, and so there's cost per kilowatt or cost per unit power capability, cost per energy storage capability, and then there's also what I mentioned briefly before, but may have been missed, is cost of the levelized energy throughput. So those of you maybe familiar with the levelized cost of energy, there is a corresponding metric calculated in a similar fashion to, but not directly comparable to, which we call levelized cost of storage. And so I would say that those are probably the three cost metrics that we get asked about most often. Battery costs, of course, also range in what's included from an individual cell level. So let's imagine the cell is a AA battery. There's a battery pack level, so you can imagine, a battery pack you might put in an RC car, let's say, and then the full system level, which would be, if I just could use that analogy again, the battery pack and a charger and the motor that's running, etc. We typically look at the equipment costs of that entire AC energy storage system. So that would include the cells, the power conversion system, the controls hardware and software, and all of the stuff that put it together, the balance of system, balance of plant. I would say right now, prices for battery systems in the megawatt scale are going to, for all equipment out to 480 volt AC output, are probably in the range of 500 to 750 per megawatt hour or per kilowatt hour. So 500,000 to 750,000 per megawatt hour. And then this varies depending on how much power is associated with it. So is it a 1 megawatt 1 hour battery? That's 1 megawatt hour. That would of course be different than a 1 megawatt 2 hour battery, which is 1 megawatt 2 megawatt hours. But yeah, in that 5 to 750,000 range per megawatt hour for this type of system. I believe this particular project was 2.7 million in total, and that ends up being around 650 or so per kilowatt hour, if I recall correctly.
Okay, thanks. And I guess this is kind of related. Somebody wants to know, how will this project impact electricity costs for ratepayers? I don't know, Sean, has anybody done that calculation?
That's the driver behind the whole thing. We expect our rate. I'll give you a quick example on our capacity cost, our transmission costs over the last 5 years. We're about going back to 2010. Our costs were about $583,000 a year for transmission costs. Going into 2007, we're going to budget $1.3 million. That increase, $700,000 to $800,000. We're looking to lower that with our capacity cost and our R&S rates to drive both of them down. So I think they'll see a substantial savings that we'll realize for the ratepayers. And with the work of Ray's done, that you can identify those critical hours to operate, we see a substantial savings. All the savings gets passed on to the ratepayers, so I think they'll see a substantial savings.
Okay, great, thank you. And I think this has to be the last question. It's kind of a couple of questions put together. Somebody wanted to know what provisions were being made for the disposal or end of life of the system, and somebody else wants to know what's the life expectancy given the number of cycles that this system has.
Yes, I guess I can go. All right.
I was just going to say that we had calculated the end of life to be 10 years, but there'll still be plenty of usable life. I think left. We plan on having 3 megawatt hours still available by then. So I think there'll be plenty of usable life even after what we calculate to be the end of the project life cycle. So, Roger, you can go ahead and add to that.
Yeah. So, thanks, Scott. So, yeah, it's designed for 10-year operation, and the guaranteed, I think, 3 megawatt hours of energy storage within that. The power rating is going to be flat out to 2 megawatts for the entirety of that term. The remaining life after that will be dependent on what we would consider an end-of-life condition, which typically is about 70% of initial energy storage capacity, after which the battery will continue to run, but the likelihood of the capacity fade or energy storage capacity fade, which is how much does it degrade over time, the rate of that will start to increase. And that happens with all lithium-ion batteries. You can imagine using your smartphone where you've got a full days of use, and then over the course of maybe a month, and you go down to just an hour or two. That's what we call in the lithium-ion battery world a rollover case, and that's a battery reaching its end of life. Now, typically that degradation is pretty much linear to about, depending on the battery type, 80% down to 70% of initial capacity. Past that, the likelihood or probability of it rolling over or increasing in its fade rate go up. And so it doesn't mean that it is at end of life at that point. You can still use it, but the likelihood of it continuing to fade at an increasingly fast rate go up after you reach that initial, say, 70% or 80% of initial capacity.
Okay. Well, I want to thank everybody who presented. I want to apologize also to those who asked questions that we didn't get to. We did have we had more than 250 people on this webinar, and despite our extended hour-and-a-half period, we just couldn't get to all the questions. We did the best we could, and I'm afraid that this is the extent of it. But we will have a related webinar in just 2 days on the Massachusetts energy storage study that just recently came out and the related policy and program recommendations coming out of that study and legislation that came out around the same time. So I think you can see that on your screen now. That's coming up on Thursday, October 27th from 3 to 4:30 p.m. Eastern Time, and it will include speakers from the Massachusetts Department of Energy Resources, the Mass Clean Energy Center, Alivo Analytics, who did the modeling analysis for that state of charge study, Customized Energy Solutions, who also wrote the study, and also comments from Dr. Emery Zhuk from U.S. Department of Energy and Dan Borneo from Sandia National Laboratories, who's here with us today. So I hope that anybody who's interested, you have registered. If you haven't, please do that. It's another free webinar, and it's just in 2 days from now. I think you'll find it quite interesting. And Samantha, any last words here?
Thanks, Todd. Well, there's some more information on your screen about where you can find out some more info and resources from ESTEP, and there's also contact information there. And we hope to see you at our webinar on Thursday. Thank you, everybody, for joining us.
Okay, thanks.